Now, if we're going to take a look at something called EMF, EMF is the absolute maximum amount of energy which is supplied for every coulomb of charge that passes past the cell. I like to think of it a little bit like a charity. Charity, here it is, and this is like the battery, all right? It is able to maximally, all the money that comes into the charity, let's say 1,000 Rand came in. And so it could give 1,000 Rand to the baby's home, let's say. But it can't really, because the people in the charity draw a little bit of a salary as well. So maybe they need 100 Rand, and only 900 Rand can go to the actual charity. So what's happening is we've got some money, a maximum amount, that is called the EMF, the 1,000. Internally, the internal, and we call it internal resistance, in other words, the need for the battery to actually move charges through itself, is going to, let's say, draw 100 Rand, and only 900 Rand will be left to the charity, or, if you like, the external circuit. Let's see how that works out as we do some more examples. So, if a cell is marked 1,5 volts, that is its EMF. That is the maximum amount of energy it can do to every coulomb of charge. The EMF is measured by connecting a voltmeter across the terminals of the cell when it is not supplying current. In other words, it's not having to give anything out or anything like that. So in other words, if all the green was gone, the EMF is the 1,000 Rand that's sitting inside the charity, before we've had to pay any administrative costs to get it through the charity in order for something to come out the other side. So I measure the EMF by putting a voltmeter across an open circuit. No current is flowing. The minute I flow current over here, this battery is going to require 1 volt itself. So its EMF hasn't changed. Its EMF is still 6 volts. But it uses 1 volt itself before being able to deliver 5 volts to what is called the external circuit. Some people call this the terminal potential difference. In other words, the potential difference across the terminals, and it tells me how much energy is being used by the external circuit. The internal circuit is inside the battery, and it uses 1 volt. Why does it use 1 volt? Because it has something called internal resistance. In other words, it actually is hard work for the charges to make their way through the battery itself. So let's look at this concept of internal resistance. The lost volt represents the quantity of energy per coulomb that was transferred to the cell. Why? Because the cell also offers some resistance to the charge, and we need to do a bit of work, in other words, 1 joule per coulomb, in moving the charges through the cell. The resistance of the battery or the resistance of the cell is called internal resistance. It is inside the cell. If I connect cells in series, I increase the internal resistance. And if I connect cells in parallel, I decrease internal resistance, because remember, resistors in parallel have got less resistance than just one resistor. And this is another reason, up until now we've never discussed it, we've only said that the only advantage of connecting cells in parallel would be because we want them to last longer. Remember, they last longer. The other advantage of connecting cells in parallel is that you decrease the internal resistance of the battery. As cells become flat, you find that their internal resistance increases. In other words, it is more and more difficult to move charges through them as they become flat. I'm going to talk about this concept of voltage, or its potential difference is another name. If I add up the potential difference of the external circuit as well as the internal circuit, so we're going to have, this should read internal, sorry. So it's going to be the load, which is your external, in other words, what's going on in the actual circuit, plus the internal resistance is going to equal the EMF. And in other words, what have you got? How do I work out the potential difference of the external circuit? I am going to say current times the series current multiplied by the external resistance gives me the external potential difference. The series current multiplied by the internal resistance gives me the internal potential difference, or another name for this is lost volts. And when I put those two together, we get the EMF. Let's look at an example. We've got a circuit represented below, and I'm going to do my little color thing. That switch is going to get closed in 2 seconds, so I'm just going to go over that switch. I'm going to go across to there. And notice I just go straight through the ammeters and I ignore the voltmeters. The circuit has got a lamp, it has got a battery which has an internal resistance of 5 ohms. So that's very important. And the reading on the voltmeter decreases by 4,5 volts. So I know that the lost volts, in other words, the energy required per coulomb of charge by the battery is 4,5 volts. What causes that decrease in the voltmeter reading? It is the internal resistance, which uses some of the energy before it is available to the external circuit. Calculate the current of the battery when the switch is closed. The fact of the matter is that I do not have the EMF of this battery. I do not even have this voltmeter reading. What I do have is I have the internal resistance and the potential difference lost to the cell. Those two things are happening inside the battery. So I'm going to say that current inside the battery is equal to the potential difference inside the battery divided by the resistance inside the battery. So this is my lost volts, and that's my internal resistance. And I find that it's 4,5 divided by 5, which is equal to 0,9 amps. Where is that true? That is 0,9 amps anywhere on the main branch of the circuit. So we want the current in the battery. We can use the information about the battery in order to get that information. Now if I want to work out the EMF of the battery, I have to work out the resistance of the entire circuit. So I'm going to go 1 over R parallel is equal to 1 over 30 plus 1 over 20. Lowest common denominator is 60. I'll end up with 5 over 60. 30 goes into 60, 2 times 2, 20 goes in 3, and you'll end up with 5 over 60. So R parallel is equal to 60 over 5, which is 12 ohms. That means that this has been reduced to 12 ohms, if you want to think of it like that. And therefore, the total resistance of the entire circuit is going to be equal to 43 plus 12 plus, don't forget about the 5, and therefore we land up with 60 ohms altogether in the circuit over there. Right, then you can say, I know the series current, so I can say that EMF is a potential difference. It is equal to current times resistance. But which current? The series current multiplied by the total resistance of the entire circuit, internal and external, and then I will be able to get EMF, internal and external, and I'll end up with 54 volts. What is the reading on the ammeter when I close the switch? So hopefully the switch was closed already. Yeah, we closed it. There we go, thankfully. And then what is the reading on the ammeter when the switch was closed? This ammeter, by the way, is sitting on a series branch. So at least a parallel branch. I'm going to put a secret voltmeter in over here. And I'm going to work out the potential difference on that parallel voltmeter. I'm going to say V is equal to I times R. I can use all the current because the whole parallel network needs all the current. The parallel network's resistance is 12, and therefore I land up with 10,8 volts. Once I've got that 10,8 volts, I'm in a position to say that I would like to know just the top branch. So I'm going to look at this 30 ohm resistor, and I am going to say current is equal to potential difference divided by resistance. The potential difference of the top branch is 10,8. The resistance of the top branch is 30, and therefore I land up with 0,36 amps. That's a slightly neater version of all of what I've just done.